So remember, if you have any questions, just unmute yourself and ask me. It's really helpful to have some sort of back and forth rather than me just talking. So if something confuses you and you don't understand it, please just let me know so I can explain it in some other way. This is a live session, so take advantage of that. That it's live, that you can ask something if you're feeling lost. Alrighty. So chapter 6. The first part in chapter 6 talks about logarithms and decibels. You don't really need to know that. You don't really need to know logarithms. Decibels, what you need to know about decibels is 3 decibels and 10 decibels. Those are the 2 decibels that you should know. They may ask you about 6 decibels, which is 3 decibels, right? Like 3 decibels plus 3 decibels give you 6 decibels. But again, it's not really worth going into that, because if you happen to fail the SPI, it's not going to be because you did not know what 6 decibels was. That's the little things. So I'll just go over the 3 and the 10 decibels. So 3 decibels is when something is doubled, and 10 decibels is when something is times 10. So obviously the one that's 10 decibels is very easy to remember because it's times 10. And the one that's 3 decibels is doubled, so that's always a little tricky one to remember. But it's just something that you just have to remember just in case they ask you. So they'll say, oh, a wave increased by 3 decibels. Let's say the strength for the wave was 3 watts. That was the strength of the wave. And it increased by 3 decibels. What is the new strength for the wave now? Well, it's just 3 watts doubling, so it's 6 watts. And then that would be the answer. And there isn't really any math in the SPI. If there is, it's very simple math like this. When something gets multiplied by 2 or divided by 2. Now, these are positive decibels. So you see that they are increasing the strength or amplitude of something, right? Multiplied by 2 or multiplied by 10 is increasing. You also have negative decibels. And it's -3 and -10 decibels, okay, which are the opposites of +3 and +10. So always look at relationships, right? Because even numbers have relationships. So if +3 decibels is going to increase, -3 decibels is going to decrease. Just the opposite, right? The opposite of positive is negative, and the opposite of increasing is decreasing, okay? So what is -3 decibels going to decrease by? The opposite of doubling, which is cutting in half, okay? Because I can make any whole number into a fraction. So doubling is 2/1, because if I do the math, 2/1 is 2, okay? And that's when you double. So I can make any whole number into a fraction. So this is 2/1. And the negative, which is the opposite of the doubling, will be the opposite of this number, which is 1/2. See how it just gets flipped? All right. So the -10 decibels is the same thing. When it's positive, it's multiplied by 10. When it's negative, it's 1/10, which means it makes the number smaller. Okay, so these are really the only 2 decibels that you have to know. If you know the positive ones, you can figure out the negative ones. Okay, because it's just the opposite, effect. So doubling, cutting in half, multiplied by 10, divided by 1/10. So that's really just the decibels, just to kind of make sure you know a little bit of it. Now here's the concept that you have to know: attenuation. Okay, and this concept is pretty cool. Okay, it's pretty cool because everything in life experiences attenuation, not just physics, right? Physics is a natural phenomenon. And if you want to get really philosophical, which I like to get really philosophical and existential, physics being a natural science, it falls within the the subject of just like things in nature, right? Like things that happen in nature, natural phenomenon. And if things that happen in, for me, you kind of always have to look at nature because whatever happens in nature happens everywhere else. That's kind of like the way I feel about things. So attenuation in sound waves has one clear definition: weakening. That's all attenuation is, weakening. Because we're talking about ultrasound waves, then we're going to say that the wave is weakening. The sound wave is weakening. So that's your definition of attenuation. Try to always have very simple definitions for concepts, because if you have a very simple definition for a concept, you will never get confused. I often ask students, what is attenuation? And they're like, attenuation is when like the wave is, doing this because you have, absorption and, and I'm like, okay, that's not a clear definition. So I can easily confuse you if I just start asking you stuff about attenuation. But if your definition of attenuation is my wave gets weaker, that's it. My wave gets weaker. Boom. I cannot confuse you if that's your definition. You always refer back to that. Your wave gets weaker, your wave gets weaker, your wave gets weaker. So that's attenuation. And if you ever like attend a party and you have the speaker really loud and you over here trying to study, right? The music is going to be very loud and you won't be able to study. So then what do? You move a little bit farther away from the speaker, but you can still hear some of the sound. So what do? You move really far away from the speaker and now you don't hear anything. Now, does that mean that someone turned the speaker off? No, it doesn't. So how is it that the speaker is as loud as it always was, yet you don't hear it anymore? Okay, that's attenuation. These sound waves have to travel a distance. Okay, and as they travel the distance, they get weaker. That's attenuation. And eventually they get so weak that they don't reach you, almost as if nothing was going on. There was no music to begin with. Okay, that's attenuation. And when I say that everything in life experiences attenuation, I really mean everything in life experiences attenuation. For instance, you fill up your car with gas and you start driving around, your gas depletes the more you drive. That's attenuation. A different form of attenuation, of course, because we're talking about gas now, but nonetheless, it's attenuation. When you're with someone for a very long time, like you're dating, and when you're with someone for a very long time, in the very beginning, you had all the patience in the world. But after 3, 4, 10 years, your patience grows thin. And now any little thing is an argument, right? We've all experienced that. I'm assuming that's attenuation. Your patience grew thinner. It wasn't as strong as it was before, your patience. Now it's really, really weak. Any little thing sets you off. And then one of my favorite examples is aging. We all grow older. Even if we don't want to, we all grow older. And as we grow older, we get weaker and weaker and weaker. I scan echo. So I see the hearts just not as strong as they were when they were younger. So that's attenuation. Just things progressively get weaker if you just leave them to their natural, not natural state, but to their natural being, I guess, for lack of a better term. Things just get weaker and weaker and weaker. All right. So enough about attenuation. So attenuation is you becoming weaker. Then the question becomes, how do you become weaker, right? What's making my wave become weaker? So the book tells you that there are 3 things that makes your wave get weaker. You have reflection, scattering, and absorption. So these are the three ways these are the three ways your wave gets weaker. Okay. Reflection is everything that comes back to you. All right. And when I get into impedance, I'll talk a little bit more about reflection and how that works and why it makes your wave weaker. Scattering is when a wave hits something, usually gas, like air, and when it hits that gas, that air, it scatters in all directions. So this one wave gets split. So it just gets split in multiple waves and all being scattered in different directions. So it definitely weakens this wave because this wave now just got split. Okay. It's like you grabbing a piece of rope and then you start undoing it. So the rope, when it was all tied together, braided together, it was a strong rope. But when you start taking it apart, it starts to become weaker, right? And now you can eventually break it. So interesting thing about hair, like it's very easy to break uh like one strand of hair. Like it's super easy to break a strand of hair. But if you grab a whole bunch of hair, like a ponytail of hair, you can probably you can probably drag somebody, depending on how small they are. You can probably drag somebody if you grab like a ponytail of hair. And then that's the concept. When it's together, it's really strong. When it's separated, it's really weak. So that's kind of like what's happening to this wave. When it leaves the transducer, it's nice and strong, but when it gets scattered, it gets split. So this wave doesn't make it to the other end. Why? Because it just got split in all directions. But again, I'll talk a little bit more about that because it's more about in reflections and attenuation and bone and stuff like that. And in absorption is your Alara. This is where you have tissue heating and the thermal index. Okay, but there's a chapter for that, so we don't need to talk about that now. So these are the three ways that you can experience attenuation. All right, so attenuation is your wave weakening. And how does this relate to ultrasound? Like, what's the whole idea of attenuation in ultrasound? Well, here's your transducer right here. And you always remember everything, excuse me, everything is relative to the transducer. What do I mean by that? When I say shallow, not when I say shallow, when we say shallow, it's because we are close to the transducer. When we say deep, it's because we are far from the transducer. So everything is relative to the transducer. This is your source. So whenever you talk about things, it's always about the transducer, like how far or close you are from the transducer. All right. So a wave, when it first leaves the transducer, it's strong because it just left, right? And as it travels, it gets weaker and weaker and weaker and weaker and weaker and weaker and weaker. All right. That's no different than you going for a run. You just started running, you have all the energy in the world. After a lap or 2 or 5 laps, now you're weaker. You put more distance in, you experience attenuation. So this is what's happening to this wave, all right? And a strong wave will give you a strong reflection, okay, essentially. And then a weak wave will give you a weak reflection. All right. A strong wave has more energy, so it can expend that energy into a reflection. All right. It makes things appear brighter. So a strong wave giving you a strong reflection will appear brighter. A weak wave giving you a weak reflection is the opposite. It's going to appear darker. So this is how you get that brightness in the near field, darkness in the far field. It's because it's the same wave, but it's the same wave, but it's a different strength of the wave seeing it. So the superficial part It's a strong wave. The deep part is the same wave, but it's the weaker version of it. Okay, because it ran through all those tissues, and every single tissue that it ran through, it experienced these three things. So imagine how many tissues are in between the near field and the far field. And every little tissue in there got a little piece of it through absorption, scattering, and reflection. Okay, so no wonder the wave experiences attenuation, because it's every little tissue's taking a little piece of it. So the big takeaway from this attenuation is how things look. So in the near field, they're going to look bright. In the far field, they're going to look dark. Now here's the thing. Let's say you have two masses, one in the near field and one in the far field. These two masses, naturally, without you doing anything, any adjustments or anything, these two masses are going to look different. Okay, they're going to look different because the superficial mass will be seen by a strong wave and the deep mass will be seen by a weak wave. Okay, so one will appear brighter, another one darker. If you say that these two masses are different, you would be right and wrong. Okay, you would be right in the sense of they do look different and your eyes can deceive you because, you know, if they were identical, they would be the same shade of gray. Granted, you know, I get that. So that's the part that you kind of are right about. But the other part that you're wrong about is you're not comparing apples to apples. This is like asking somebody with 20/20 vision to look at this mass and then asking someone who's legally blind to look at this mass. It isn't a fair game. So what you must do is you have to even out the playing field. You have to make that wave that is strong in the near field be equally as strong in the far field. Okay, that way you can have an even playing field, and then you're able to compare things to each other because now you have pretty much like the same wave. So what helps you do that are the TGCs. Okay, TGCs is time gain compensation. Time is that 13 microsecond rule. And that 13 microsecond rule is associated with depth. Every 1 centimeter is 13 microseconds. So every centimeter has a timestamp, you know, attached to it. So that's why they're using time. Gain is the level of brightness. You can either make things brighter or darker, but you're adjusting the level of brightness. It doesn't just mean, oh, things get brighter. It means you are adjusting the brightness level. So you can make it get brighter or you can make it get darker. That's the brightness level. And then C is for compensation. Okay, so there are two different definitions, right? Compensate is to like pay, and then to compensate is to make up for. You know, so the the funniest example that I always think about is um it's, you know, and I don't mean to be like stereotypical or anything like that, but it's always funny, and you always see it in reality TV, how you have like this like absolutely gorgeous girl, and she dates like this average looking guy, and you know, people will ask like, why are you with this average looking guy? You know, he's like, you're too pretty for him, blah blah blah. And then she'll say, oh, you know, he's very caring, he's very romantic, he's a great husband, a great father. So he makes up for that. You know, his the way he is compensates for his lacks of good looks, right? So for the TGCs, that's what they're doing. They are compensating, trying to make up for the fact that your wave attenuated. So they're trying to help out the wave pretty much because they know that it attenuated. So then what you do is you have this TGC curve. Actually, I shouldn't draw it there. I should draw it next to here. You have this TGC curve here, and you'll notice that you don't really adjust the near field. because the near field does not need any compensation. It didn't lose anything. Why would you need to help it out? But as you go deeper into the body, you realize that the wave is experiencing more and more attenuation. So you give it a little bit more and more help. So eventually, you want this strong wave to be the same down here. And once you do that, then you have an even playing field. And now you can compare your masses, and who knows, it might be the same kind of mass. So it started out looking different, but after you did this, you're like, oh, wow, yeah, it's actually the same kind of mass. Okay. Does that make sense?
Can I ask you a quick question?
Yep.
The TGC, is that on the right hand side of the machine? And when
Normally it
you're
is.
and when you're changing it, when you're shifting it around, that means you're changing the T, the what is it? I forgot what the T stand for, but the
Time.
G gain and the C compensation. That means you're changing everything at the same time when you're changing those levels.
Yep. Yep. Because you're
Okay.
changing the brightness level at different depths, and that's the time.
Okay, time, yes.
Yeah. Yeah.
Okay.
So you can change it at a very specific place, or several places. Some you don't have to touch. So it's very, very specific. Okay.
Okay.
Which is very different than this guy, your gain. But later, there's a chapter where I'm going to talk about the receiver functions. So I'll bring up gain versus TGC. Does anyone have any other questions? Does this make sense?
It makes sense.
Okay. Now let's get into reflections. So these are more like concepts to know, not necessarily things you'll be tested on. Attenuation you will be tested on. So that's definitely one thing you'll be tested on. Actually, before I move on, they talk about depth and frequency affecting attenuation. Okay, let me write this down. Depth and frequency affecting attenuation. And it just means that if you go deeper, you have more attenuation, which is kind of like what I explained now. And as the wave travels, it just gets weaker. So that's depth, that's more distance, okay? So the more distance there is, the weaker you get. And just think about running. The more you run, the weaker you're going to be. That's it, nothing else. Then you have frequency. Now here you have high frequency versus low frequency. And they're saying that if you have high frequency, you have more attenuation. And if you have low frequency, you have less attenuation. Okay, this is the concept of like high frequency has to be shallow, and then low frequency can go deep. Okay, this is why, because if you have high frequency, you have more attenuation, meaning that you get weaker more quickly. Okay, so if you get weaker more quickly, you cannot go the distance because you got weaker very quickly. So you die out much quicker. If you have less attenuation, it means that you're getting weaker, but at a slower rate. Okay, this right here is your marathon runner. Marathon runners can go a very long distance. Sprinters cannot. If you have a sprinter, they run really, really quickly for a short distance, and then that's it. They expend all of their energy. They just waste all of their energy in that short burst. But if you have a marathon runner, they can go a very long distance, okay, because they get weaker, but at a very slow rate. All right. So here's the price that you have to pay when it comes to these guys. Because attenuation has a little formula, which is called the attenuation coefficient formula. and it's frequency divided by 2. Okay, if you draw that imaginary line that I taught you all yesterday, this is your top, and everything on top is directly related. So if I have more frequency, I have more attenuation. Okay, so the formula proves it. The formula tells you that yes, this is true. Okay, so here's the trade-off. If you have a higher frequency, okay, you get more detail, a prettier image, but you have to be shallow because you get weak, you get very weak. And if you have low frequency, you get less detail, but you can go deep, okay, because you get less weak, let's just say. Okay, a way to remember this is parenting. And again, not to be stereotypical, it's just, you know, this is what we commonly know about, you know, husbands and wives, moms and dads. Your high frequency is your mom. Your low frequency is your dad. Okay, why is that the case? Because moms tend to be like, if let's say that you're babysitting, a mom is going to be like very, very attentive to the baby. Generally speaking, right? Let's not take anything personal. Moms tend to be very attentive. Okay. So if you ask a mom, you know, what did the baby eat? Did the baby sleep? This and that. The mom can give you all the detail about the day. Okay. But it comes at a price. It is very exhausting. So when you are very alert and you're very attentive for a very long time is exhausting. It really is. Low frequency of the dad. Why? And this is coming from a guy's perspective, right? Just my perspective. We're a little bit more laid back. So if we're watching a baby, you know, we're just making sure the baby's alive. That's it. That's like our job, to be honest. So if you ask us, did the baby eat? Yeah, the baby ate. Did the baby sleep? Yeah, the baby slept. What did the baby do? The baby was the baby. It was a baby, and that's it. You know, that's our, I don't know. That's the way we do things, generally speaking. So we give you less detail about the day. Okay. But because we give you less detail and we're more laid back, we're not very tired. Right? A dad can go out later that night. A mom can't because a mom is exhausted and a dad isn't. Okay. So that's sort of how high frequency and low frequency works. High frequency says, I'm going to give you all this detail. I'm going to show you every little tissue, how big it is, how small it is, what grayscale it is, any masses. I'm going to give you all this detail. But because I'm doing that, I'm going to get really tired. And because I get really tired, I do not go very far. I stay shallow. And then low frequency says, listen, I'm not really going to give you all this detail. I'll show you what's there, blah, 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 but I'll go a long distance. So I'll show you things that are really, really far away. Not in great detail, but I'll show you things that are really, really far away. So your job is to know which one to pick, depending on what you're doing. Okay. If you're scanning a kidney, you can scan a kidney subcostally here. You can put your transducer here and you can scan a kidney, and that kidney is going to look like this. It is going to be deep. So in this case, it's better to use low frequency. Generally, it's better to use low frequency. Okay, because you need that wave to make it back there, to make it down there, excuse me. Because if you were to choose high frequency, you'll see maybe up to here. And right here, it'll be way too dark. So what's the point? You're trying to see the kidney. What's the point of getting all this detail in the liver and not even making it to the kidney? You know, there's no point. So then you opt for the low frequency. But here's the thing. You can move your transducer laterally. And guess what? The kidney's right there. So now you're going to see this. Your kidney is now shallow. And if you stay with the low frequency, you're making a mistake. Your circumstances have changed, so change with them. You're no longer having to sacrifice and say, oh, you know, this is far away, I have to use low frequency. No, no, no. Your kidney is now shallow. Take advantage of that and switch to high frequency. Even though high frequency, the limitation is shallow, what you're looking at is shallow. So it doesn't matter that that's a limitation, you know, because what you're looking at is shallow to begin with. So as your circumstances change, you change with them. And that's the whole idea of instrumentation. You changing little things here and there as your circumstances are changing. Okay, you have to adapt. That's the name of the game for instrumentation. Does that make sense? Any questions? Are we good? Are we alive? Hello?
We're good. That was great.
Okay, okay. All right. One little thing for you to know is Rayleigh scattering. And trust me, you will get a question on this. And it's just something for you to know. It's frequency to the fourth. That's all you have to know. And this is for blood. It's scattering for blood. Okay. But all you have to know is the name Rayleigh scattering and that it equals frequency to the fourth. Okay. And a simple question that maybe you could get is your frequency doubled. And they want to know what happened to your Rayleigh scattering. So if your frequency doubled, it actually doubled to the fourth. So your Rayleigh scattering is 2 times 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. So your frequency doubling, your Rayleigh scattering got multiplied by 16 times, you know, which is huge. Okay. So again, just know that this exists because the question that you may be asked is simply that, like, oh, what relationship, you know, is for frequency to the fourth, or Rayleigh scattering is related to frequency. How, you know, it's directly related to the fourth. So just knowing this little formula here is all you need to get you through that question, because it's a very straightforward, you know, question, like a filler question that they will have in there. All right. They have a half value layer thickness, but that's something that I go over if I have time. And I never saw it on my exam either, so you know it's fine. Now, there are different forms. Should I go into reflections? Yeah, there are different forms of reflections. Okay, different forms of reflections. And this is just for your knowledge. You have specular, which is pretty much very predictable. It goes and comes back in the same direction. Or if it goes at an angle like this, it bounces back in that same opposite angle. You know, imagine like you're tossing a ball on a wall. You toss a ball straight to the wall, it bounces back straight. You toss it aiming down, when it bounces off the wall, it also continues going down, okay? Which is pretty much this. So these are what we call specular reflections. You have to have a smooth surface for this. Okay, so it's just kind of like a little definition thing. The one that actually happens mostly in the body is diffuse. Okay, diffuse reflections. Those are the ones that happen mostly in the body. And those happen when you have a rough surface. And it's basically a wave going like this. And when it hits that surface, it bounces back, but it kind of bounces back in different directions. Diffuses, kind of like spreads out a little bit. Okay. So just little definitions for you to know. reflections. I don't think the test asks about that. If anything, sometimes they ask about specular reflections, which is like the best one. The best one that we don't really see. Here's a scanning tip. If you ever see something funky over here and you want to investigate it, don't investigate it while it's on the side part of the image. Okay? Because when you do that, you send out a wave and this wave reflects back, but it reflects back in very different angles. Okay? And some of these reflections never come back to you and others do. And every reflection carries a piece of information. Okay, so these reflections right here, they're going to go this way, but your transducer is up here. So whatever information these waves carry, you never get them back. Okay, so what do you do when you want to investigate this? You move it towards the center. You know, you heel and toe your transducer or you move your transducer. That way this little funky mass gets moved towards the center. And now a wave can go straight down and it can come back very strongly. And you can create a specular reflection. Okay, this will be normal incidence, 90 degrees normal incidence. So it's just a scanning tip. Anytime you see something that requires investigation, put it in the center of your image, in your main beam axis. All right. Impedance, very important concept. Okay, you may be asked questions about this. So it's very good to know it. Impedance has a formula, and it's density times propagation speed, which is the letter C. Okay, remember everything is on top, so everything's directly related to impedance. If my density goes up, my impedance goes up. If my density goes down, my impedance goes down. If my propagation speed goes up, my impedance goes up. If my propagation speed goes down, my impedance goes down. And these two do not affect each other. If my propagation speed goes up, density does whatever the heck density wants to do. It is not affected by propagation speed. So just always remember that. So what is impedance? Like, what is the concept of impedance? Impedance tries to prevent transmission. Okay, so that's the simple definition. It tries to prevent transmission. Okay, so here we get to the concept of what is transmission and reflection. Tissue 1, tissue 2, tissue 3, tissue 4, tissue 5. So transmission is what happens when a wave leaves the transducer and it goes from one tissue to the next, then from the next to the next, then from the next to the next. That is transmission, which is very different from reflection. Reflection is when a tissue goes, it hits a boundary. They call it a tissue-tissue boundary. That's the fancy way of saying two tissues are touching. And in there, it creates a reflection that is sent back to the transducer. And then the rest of the wave keeps going, okay, which is transmission. So transmission and reflection are kind of pretty opposites. Transmission keeps going, reflection comes back. So impedance tries to prevent transmission, okay? It is like the blackout curtains, all right? When you use blackout curtains, what is the purpose of blackout curtains? To prevent the sun from getting inside your room. That is transmission, okay? The sun over here has the sunlight, and then here's your window, okay? And then if this sunlight hits your window and goes through, that is transmission. It went through. All right, and then what is the purpose of blackout curtains? The purpose of blackout curtains is to prevent transmission, to reflect all of that back or to absorb it. But the whole point is it's not supposed to let light into your room. It's preventing transmission. Okay, that is what impedance is. It's the same thing as having a bouncer at a club. Bouncer at a club is your impedance. If it's like a really tough bouncer, he or she is not going to let you in. But if he or she is a really nice bouncer, they'll let you in. Okay, so impedance is that, and it's determined by density and the propagation speed of each tissue. So different tissues have different values for impedance. Impedance is the units of rails, and it can be shorthanded by the letter Z. Okay, but it's really good to understand the concept. Now, when you have high impedance versus when you have low impedance, high impedance is high impedance is high reflection. Low impedance is low reflection. Now, here's the thing about reflection and transmission. Remember that they're pretty much opposites, okay? So if they're pretty much opposites, they balance each other out. That's what they do. You cannot tell me you went to the club, 10 of your friends went to the club, and you cannot tell me that 8 of you got through and 8 of you got sent back. That makes no sense. 10 of you showed up to the club. What do you mean 8 got through and 8 got sent back home? Who are these strangers that now became part of your group, you know? So if 10 of you guys went to the club and 8 got through, that means that 2 were sent home because 8 plus 2 is 10, right? And everything balances out. So impedance is the same way. So if I have a high impedance, I have a high reflection. If I have a high reflection, I must have a low transmission. Because you cannot have a lot going in and a lot going back. No, it's a balance. If a lot went in, then only a little bit came back. If a lot came back, then only a little bit went through. Okay? So high impedance, remember that impedance tries to fight transmission. So if you have a lot of it, it's really good at fighting transmission, at preventing transmission. Okay, that is why high impedance gives me low transmission. These are my blackout curtains doing their job. Okay, the reason why I write it out with reflection is because it's very easy to remember high and high. All right, that's why I write it out with high reflection. So high impedance gives me high reflection. And if I know my reflection is high, I can guess that my transmission is low because they balance each other out. Okay, so this is where you just use your common sense by looking at the patterns. So you don't have to remember all of that. And then to figure this guy out, you just do the opposite. If high impedance is high reflection, then low impedance is low reflection. And if I have low reflection, I have high transmission. Okay, because a little bit got reflected, where did the rest go? The rest went through. All right, so that's how that works, okay? So here is where I do an example about this, okay? And this is the conservation of energy. So in the book, they talk about the reflection coefficient, the transmission coefficient, Z1, Z2, I don't know, some crazy stuff in there. Don't worry about that. All they're doing is they're explaining to you that everything has to be accounted for. The law of conservation of energy, everything has to be accounted for. Okay, and here's the example for that. I send out a wave. That wave is 10 watts strong. Okay, this wave travels from tissue 1 to tissue 2, and it has transmission. It keeps going. Now, my transmission here is 9 watts. So I started out at 10. And when I went from tissue 1 to tissue 2, now I have 9 watts. Okay. That means that my reflection is 1 watt. Because if I have 9 left over and 1 got sent back, I get my 10 back. Everything is accounted for. Okay. Now the question is this a high impedance tissue or a low impedance tissue? So you have to ask yourself, how much got sent back? Did a lot get sent back or did a little bit get sent back? A little bit got sent back. That makes it a low impedance tissue. Okay, another way of thinking about that is how much went through. Did a lot go through or did a little bit go through? Did my impedance do its job or did my impedance suck at it? And my impedance sucked at it, so it's low. Okay, does that make sense?
Yes, it does.
All right, my next one is from tissue 2 to tissue 3. And here I drop down to, let's say, 6 watts. So I just do the math. I started at 9. I have 6 left over. How much got reflected? 3. Because 6 plus 3 gives me 9. And 9 plus 1 gives me 10. Everything is accounted for. Okay. And then I'll ask myself the same question. Is this a high impedance or a low impedance? And from 9 to 6, a lot of it still went through. 6 is a majority of 9. So I would say that this is a low impedance. Now I go into this tissue and I have 2 watts. 2 watts went through. Okay. So how much got reflected? I was at 6. I have 2. That means 4 got reflected because 4 plus 2 is 6. 6 plus 3 is 9. 9 plus 1 is 10. Everything's accounted for. But in this case, I'm going to ask myself, did a lot go through or did more get sent back? More got sent back. Look, 4 got sent back while only 2 went through. Okay, so that would be a high impedance. And in tissue 5, let's say that 2 watts were sent back. Nothing went through. This will also be high impedance because nothing went through. And this is normally what happens with bone. Bone doesn't let anything go through. Everything gets sent back. And that's how you end up getting a shadow. Okay, reflections are how your image is created. If you send out a wave and the wave never comes back to you, you never know what was there. Okay, you never know what was there. That's why you need reflections. So when you end up hitting bone, this wave hits bone, it gets absorbed and it gets reflected. There's no transmission. So how can you tell me what's behind bone if a wave was never able to make it there? Okay, it was never able to make it there. So it was never able to produce reflections. So that's why you end up getting a shadow behind a bone. Now here's the thing. Shadow doesn't mean there's nothing there. It only means you cannot see it. Okay, right now, turn off the lights in your room and make it pitch dark. You're not going to be able to see a thing. Does that mean that there's nothing there? Cover your eyes, lights on, cover your eyes. And you don't see a thing. Does that mean there's nothing there? No, it just means you cannot see it. So when you hit bone and you get this big shadow, sometimes it's really important to see what's behind the bone because there could be a mass there. Why not? Just because there's a shadow, you think there's nothing there? There could easily be a mass there. You just can't see it. No wave was able to go through the bone to then create reflections, to then create an image of what's behind the bone. So what do? You go around the bone. You start moving your transducer around the bone to see what's behind it. All right. So this is the concept of impedance. So the most important thing is knowing the formula. and the relationship in the formula. And remember, if you know how to read formulas, you should be able to get the relationships. No need for you to guess the relationships. Know the formula and you will just get the relationships from them. And then the second thing to know is, what does high impedance mean and what does low impedance mean? Okay, that's pretty much what you need to know about impedance. Any questions?
No, that was really good.
Thank you. All right. Now, the last concept. The last concept is the law of refraction, which is Snell's law. So the law of refraction talks about transmission. Okay, so earlier I spoke about reflections. You send out a wave like this, it bounces off like this. This is the reflection. Or if it's normal incidence, which is straight ahead, it bounces back like this. This is reflection with normal incidence. Now the question becomes, how is transmission affected? So normally when it's a straight angle like this, transmission will be very simple. Okay, that's kind of like the book just kind of gives you a little gist of it, like, oh, transmission tends to be very simple. But when you have an oblique angle, something that's not straight, transmission can get complicated. Okay, it can kind of keep going in the same angle, or it can bend. Okay, this is transmission. Okay, this is reflection. So don't confuse reflection over here with transmission over here. Okay, so remember, transmission is what goes through, reflection is what comes back. And an ultrasound is a combination of both. You send out a wave, here's a tissue, it creates a reflection, and the wave keeps going. Here's another tissue, creates a reflection, and the wave keeps going. Okay, that's what pretty much happens in ultrasound. Snell's law. Snell's law is transmission with a bend. That is Snell's law. Transmission with a bend. Simple definitions. Okay, simple definitions. Transmission with a bend. So I'm specifically talking about transmission, not reflection. Okay. There are two rules that you must satisfy in order for there to be a bend. The first rule is you must have an oblique angle. Your wave must travel in an oblique angle. What is an oblique angle? Any angle except 90 degrees. So any angle can be oblique as long as it is not 90 degrees. So is 89 degrees an oblique angle? Yes. Is 91 degrees an oblique angle? Yes. Why? Because they are not 90. And then of course you can have 3 degrees, 15 degrees, 48 degrees, every other degree, as long as it's not 90. So that's the first rule. The second rule is that there must be different propagation speeds between the tissues. Because your wave is traveling through different tissues, right? So these different tissues that is traveling through must have different propagation speeds. Now you don't have to know like what tissues have what propagation speeds and things like that. For the most part, solids are the fastest, air is the slowest, and then water is somewhere in the middle. But you don't have to really get into that. The idea is these two rules must be satisfied. Okay, so what kind of question would you get for this? The kind of question that you would get is they'll tell you that a wave is leaving at 45 degrees and that tissue 1 has a higher propagation speed than tissue 2. And then they'll ask you, what's the refraction angle? Okay, that's pretty much the gist of the question, okay? So first you have to ask yourself, are my 2 rules met? Not one rule, okay? Both must be met. So is there an oblique angle? Yes. Are the propagation speeds different? Yes. Okay. They're not telling you flat out, oh, this one's different than that one. They're just saying that one is higher than 2. That means they're different. Okay. Because if they were the same, they would just say tissue 1 is the same as tissue 2. But they're saying that they're different. Or they can give you numbers. They can say that tissue 1 is 3 centimeters per second, tissue 2 is 1 centimeter per second, and you can see that they're different. All right. Now you don't care at this point, you don't care how different they are. Like if one's higher, one is lower, you don't care. Okay. What you're concerned with is satisfying these 2 rules. If those 2 rules are satisfied, then you can move forward and figure out the refraction angle. Okay. Here's the trick though. Sometimes you might get a question where they say, they might give you, oh, my angle is 90. Tissue 1 is higher than tissue 2. What's my refraction? And then you start thinking like, okay, let me apply all the rules, figure out what the refraction angle is. It's like, no, there is no refraction. They give you 90 degrees. So just because a question tells you, hey, what's the refraction, doesn't mean that there is any. You first have to prove to yourself that there is refraction. Okay, don't take the question as being true. If I blame you because you stole my cookies, doesn't mean that you stole my cookies. Okay, me blaming you doesn't automatically make it true. So if they ask you what is the refraction angle, you first have to say, is there refraction to begin with? Okay, so then you look for what angle did they give me, and did they give me different propagation speeds? In this case, they give you a 90-degree angle. Boom, it stops right there. Okay, so what would that mean? There is no bend. There is no bend. It means that if the wave was traveling like this, the wave is going to continue to travel like this. A bend is when the wave starts like this and all of a sudden it takes a different direction. That's a bend. Or maybe they give you an oblique angle, but the propagation speeds are the same. So what happens to this oblique angle? It continues in that same oblique angle. It doesn't bend. It doesn't change directions. It continues in the same direction. So that's what it means by there is no refraction. Okay. All right, let's get to the complicated part though. Like, what if there is refraction? So they're going to give me a 45-degree angle, and they're going to give me that tissue 2 is higher or faster than tissue 1. All right. There are 4 rules for refraction. Like these first 2 rules is to figure out, is there refraction? Then you need to figure out, what is my refraction? How is the bending happening? Is the bending going to be bigger than 45 degrees? The bending going to be smaller than 45 degrees? The great thing though is you don't need to know the exact degree. Like you don't have to figure out, oh, it's 47 degrees. No. You'll see that it's just about knowing the relationship, and then the answer will pop up. Okay, you'll see that. So there are 4 rules. Luckily, you only need to know 1. Out of those 4, you only need to know 1. Because everything else is predictable. Everything else you can figure out with common sense. So the name of the game is always find the patterns, and that's what I'm here to show you. All right. So the first rule is, if the propagation speed, which is c, in tissue 2 is higher than tissue 1, my angle is higher. Meaning that my angle gets bigger. Okay, so if it's 45, my angle is going to get bigger than 45. Okay, so that's the rule. If propagation speed in tissue 2 is higher than tissue 1, my angle is higher. So I'll do a little example over here. Tissue 1 or medium 1, tissue 2 or medium 2. I'll have an oblique angle of 45 degrees. My propagation speed here is going to be 2. My propagation speed here is going to be 6. Okay, so 6 is bigger than 2. All right, so in this case, my angle is going to bend in a bigger angle. Okay, before it was like this, and now it's like this. Just to illustrate it, right? You don't have to draw things out, right? But this is just to illustrate it. So my angle is going to be bigger. Okay, so how would this look at on a question on a multiple choice? This is how it's going to look. That's it. And all you have to say is, what is happening to my angle? Oh, it's getting bigger. Okay, can it be A? No, because A means that there was no bend. It started at 45, it kept going at 45. So 45 cannot be the answer because 45 means that there is no bending. And I know there's bending. Why? Because my angle is oblique and there are different propagation speeds. Boom, cannot be A. B is 40. All right, well, let me look at my propagation speed. So tissue 2 is higher than tissue 1. The rule says that if tissue 2 is higher, angle must be higher. 40 is less than 45. Cannot be that. Now 61, okay, yeah, 61 is higher than 45, so this could be it. All right, but you always have to read all your choices, okay, so you don't stop there. And then 38, oh no, 38 is smaller than 45. I'm looking for a bigger angle than 45, so it cannot be 38. Boom, okay, my answer is C. So you don't have to figure out like what is that angle? You know? Like take out my calculator. No, no, no. If you just know the rules, the answer pops up. Because they have to only give you one angle that's bigger. In this case, right? Because the answer has to be a bigger angle. So they can only give you one angle that's bigger and the rest are going to be smaller. Okay? So that's why I'm saying you don't have to do any crazy math besides just knowing the rules. All right. So how do I make the rest of my rules? Because like, what if tissue 2 is not higher, or what if something is different, right? Or what if they word it differently? Instead of saying tissue 2 is higher, what if they worded tissue 1 is lower, or something like that, right? The reason why I always start out with tissue 2 is because tissue 2 has a direct relationship with the angle. Tissue 2 is higher, angle is higher. So I always start out with direct relationships because they're easier to remember. Now here's how I make my second rule. Tissue 2 being higher than tissue 1 is the same thing as tissue 1 being lower than tissue 2. And it gets really wordy, so bear with me, okay? Look at this down here, bottom right. Tissue 2 is higher than tissue 1. All right, we can see that. 6 is higher than 2. But can't we also say tissue 1 is lower than tissue 2? Isn't it the same thing? This is higher than this, which means that this is lower than this. It's just the same way of saying, you know, potato, potato, right? So my second rule is going to be that. It's going to be from the perspective of tissue 1. Now I want to talk from the eyes of tissue 1. So if propagation speed in tissue 1 is lower than tissue 2, my angle is higher. So don't get confused. My angle doesn't change, okay? Because you think, oh, tissue 1 is lower than tissue 2. That means your angle is going to be lower. No. Because tissue 1 being lower than tissue 2 is the same thing as tissue 2 being higher than tissue 1. So it's very wordy, but trust me, as you talk it through and you see it, it makes sense. That is why my rule right here does not change. Because tissue 1 being lower means that tissue 2 is higher. And if tissue 2 is higher, my angle is higher. Okay? I'm just writing it from the perspective of somebody else. That's all. Okay? So now I make my other rule. Now I want to know what happens if tissue 2 is lower. Because I'm talking, this is all tissue 2 being higher. What happens if tissue 2 is lower? So let's make tissue 2 lower. Now tissue 2 is lower than tissue 1. Okay, so there's my other rule. And I can take it from this rule right here. Because it's, remember the direct relationships? Tissue 2 is directly related to my angle. So if propagation speed in tissue 2 is lower than tissue 1, then my angle is lower. Because tissue 2 has a direct relationship to the angle. So now that tissue 2 is lower, my angle becomes lower. And from this rule, we make the final rule, which is what we did here. Now let's look at it from the perspective of tissue 1. If propagation speed in tissue 1 is higher than tissue 2, my angle, again, doesn't change, is lower. Because this right here is the same thing as this, which is what we did from here to here. Okay, so you only need to know these 3 rules. The first 2 rules to figure out that there is refraction. And then the last rule, because from that last rule, you can make this one, and this one. Just by knowing that first rule right there. Okay, just by knowing that first rule, you can figure out the other one. Okay, does that make sense?
It does.
It's very wordy, okay? I give you that. It's very wordy.
It's the same thing, though.
Yeah, it's just the same thing
They're
repeated.
the same rules, just written.
Right, from the eyes of somebody else.
Yeah.
Okay, and that's why I'm saying you only need to know that first star, because from that first star, you can figure out the rest, okay? This is no different, honestly, this is no different than you having 2 friends. One friend is a liar and one friend is honest. Okay. If you can figure out the liar, doesn't that also mean you figured out the honest one? Right? That's the way it works. It's process of elimination, right? If you figure out one, you figure out the other. So it's the same thing with these rules. Once you know one rule and what that rule says, then you can figure out the rest of the rules because it follows a predictable pattern. Okay. There is a pattern to it. And that really helps to like not study as much when you just know, like study this and then you can figure out the rest. Alrighty, that's the end of chapter 6. Let me